Hello, I'm Lindsey Leach and welcome to part 2 of Chi-Square Essentials. In part 1, I showed you how to use the Chi-Square goodness of fit test to see whether the data for a single categorical variable follows a hypothesized distribution. Here in part 2, I will show you how to use the Chi-Squared test for independence, or the Contingency Chi-Squared test. This test is used to see whether there's a relationship between two categorical variables. Imagine I breed Labradors and you're coming to see me to choose yourself a new member of the family, a beautiful Labrador pup. You can choose a black, a chocolate or a yellow pup. What if this choice was influenced by factors like your gender, your age or your personality? And how could we test if that were the case? I have collected some data on the age range of my customers and which colour pup they go for, as shown in the table. By looking at the raw numbers, it appears that my younger customers are much more likely to choose a black or a brown pup, while my older customers are more likely to choose yellow. Are these patterns in the data simply down to chance, or do I have evidence there's a real relationship between colour choice and customer age? To answer this, I need to test the null hypothesis that there's no relationship between pup colour choice and age, i.e. the two categorical variables are independent. This is where the Contingency Chi-Squared test comes in. The first thing I do is add up the numbers to give row totals and column totals, as well as an overall grand total. From those totals, I can calculate the expected numbers in each cell of the table, here shown bracketed in red. For example, how many of my customers in their 20s would I expect to choose a black pup if my null hypothesis is true? I multiply the fraction of people in their 20s, which is 60 over 200, by the total number of people who chose a black pup, which is equal to 95, to give an expected number of 28.5. In other words, what I have done is to multiply the row total by the column total and divide by the grand total. The expected number for every other cell in the table can be calculated in the same way. Then I calculate the Chi-Squared statistic to quantify how much difference there is between observed and expected counts across the whole data set. For each cell of the table, I calculate the square of the difference between what I expect to see and what I actually observe and scale it by the expected number. The results are shown in blue in this table, and I suggest you pause the video now and check to see if you can obtain these values yourself. The sum of all these values in blue gives me my chi-squared value of 38.3. This is a very large chi-squared value, but I still need to check in the probability tables to see if it is significant at my chosen probability level. To do this, I calculate the number of degrees of freedom, using the number of row options -1 times by the number of column options -1. Here, this is 3 minus 1 times by 3 minus 1, which equals to 4. At the 1% level, the critical value in the chi-squared probability table is equal to 13.28. If my chi-squared value had been less than this value, I would have accepted my null hypothesis, but my chi-squared value of 38.3 is far higher than the critical value. I could also have worked out using my computer an exact p-value from the chi-squared value, which comes out as p equals 9.7 times 10 to the negative 8. I therefore reject my null hypothesis and conclude that choice of pup colour is significantly dependent on how old my customer is. And by looking back at the data again, I can see that my younger customers are much more likely to choose a black or a brown pup rather than a yellow one.